Energy systems, carbon capture, and sequestration. By one means or another, we've all been made aware of the consequences of humanity's ever-growing craving for energy. The release of carbon into the troposphere, oceans, and landmass is causing change in weather conditions, ocean acidification, polluted air, and much worse. Many in the scientific community believe that the average temperature on Earth will rise by approximately 2 degrees Celsius by the end of this century. The amount of CO2 we have already released is staggering. According to ice core data, in 1700 there was 278 parts per million of CO2, while in 2016 data showed that there was 408 parts per million. On top of this, in the past 58 years, CO2 levels have risen by 77%. CCS, which represents carbon capture and sequestration, involves the filtration and storage of CO2 from plant exhaust, and its history is rather brief. Around the turn of this century, governments began to impose high carbon taxes, leading to the development of the first commercial example of CCS technology, the Weyburn-Medalley carbon dioxide project. This early implementation of CCS involved the injection of exhaust CO2 into large oil reservoirs in Medalley, Saskatchewan. This project was also the first instance of commercial cross-border exchange of pure CO2 between Canada and the USA. Note that CCS technology is only about 2 decades old and is being innovated continuously. CCS involves 3 steps: capturing, transportation, and storing. First we'll look at capturing, which itself has 3 systems: pre-combustion, post-combustion, and oxy-fuel combustion. Pre-combustion carbon dioxide capturing is achieved by oxidizing combustion fuels, which will yield hydrogen gas and carbon monoxide. The carbon monoxide is then shifted into CO2, which can be captured in a relatively pure stream, and the remaining hydrogen gas is then used as fuel. Evidently, post-combustion capturing involves capturing CO2 after the plant's fossil fuel has been combusted. Flue gas, which is a plant's combustion exhaust, can be composed of water vapor, nitrogen, and sulfur amongst the CO2 which is filtered out in this process, leaving only that proportion of CO2 that was in the original flue stream. This process is less efficient than pre-combustion, but is thoroughly understood and widely used due to its capability to be retrofit to existing coal-fired plants. Oxy-fuel combustion systems combust fuel in a chamber with pure oxygen as opposed to regular air. Flue gas is injected into the chamber in order to reduce flame temperature during combustion. Since the flue stream will consist primarily of condensed water vapor and CO2, the combustion exhaust is nearly pure carbon dioxide, with a small amount of CO2 leaving the system along with the condensed water. As such, oxy-fuel capturing is the most effective system listed here, but is also energy demanding due to the initial flue gas separation process. The next step in CCS is transporting. Captured carbon dioxide is transported by pipelines, ships, road, or rail tankers, with the method of transportation determined according to the CCS project and its health and safety regulations. CO2 is stored in porous geological formations deep underground. CO2 can be in liquid or supercritical phase depending on its stored pressure and temperature. There are 3 main types of geological formations used: oil and gas reservoirs, deep saline formations, and unminable coal beds. Additional energy is required for CO2 capture, transport, and injection. Therefore, the cost of energy of a plant equipped with CCS is much higher than that of a normal plant. It's estimated that the cost of CCS is $60 per ton of CO2, with ranges of 1 to 3 US cents increase per kilowatt hour for different plants. CO2 emissions from a plant can be reduced by up to 90% depending on the plant type. CCS projects have yet to gain traction worldwide. However, the captured CO2 is projected to increase to 4 gigatons per year, and the number of projects is expected to reach around 1,800 by 2050. However, the use of CCS technology can result in significant reductions in air quality. Such air pollutants can be released as nitrogen dioxide and sulfur dioxide, with emission increases of up to 31% and 18% respectively. In order to avoid exceeding pre-industrial world temperatures by 2 degrees, CO2 emissions should be reduced by 50 to 85% by 2050. However, energy demand could increase by 45% by 2030, with fossil fuels remaining a key player for energy sources. Thus, CCS will give flexibility to increase using fossil fuels while substantially reducing CO2 emissions.